In this video, we will look at the Big Theta notation. In analysis of algorithms, we focus on the number of times the operations are performed by an algorithm using the step count method. The step count considers the frequency or the total number of times each statement is executed, and by adding the frequency of each statement, the step count of the entire algorithm is computed. Now, mathematically, the number of operations needed to execute an algorithm is represented as a runtime function f of n, where n is the size of the input. Let us graphically plot the function f of n. So, we will have n, which is the input size, on the x-axis and the running time on the y-axis. So, graphically, when the function f of n is plotted, it will look like this, where as the input size n increases, the running time increases. Let us consider another function g of n in such a way that the function c1 multiplied by g of n is less than the function f of n. And let us also consider another function g of n in such a way that c2 multiplied by g of n is greater than the function f of n after some value or input n0. If you observe, the function f of n is bounded between c1 multiplied by g of n and c2 multiplied by g of n. Now, mathematically, we can write this as c1 multiplied by g of n is less than equal to f of n, and c2 multiplied by g of n is greater than equal to f of n for n greater than n0. Here in this equation, c1 and c2 are constant and is greater than 0, and n0 is greater than equal to 1. Now, if we are able to satisfy this equation, then we can say that f of n is big theta of g of n. And this definition is called Big Theta notation. The Big Theta notation is used to describe the tight bound of an algorithm. Now, let's take an example to prove this notation. Let us consider that we have a function f of n as 5n plus 4 and another function g of n as n. Then, by the Big Theta definition, we need to find the constants c1 and c2 which are greater than 0 and an integer n such that c1 multiplied by n is less than equal to f of n and c2 multiplied by n is greater than equal to f of n for every n greater than equal to n0. That is, in this case, c1 multiplied by n is less than equal to 5n plus 4 and c2 multiplied by n is greater than equal to 5n plus 4 for every integer n greater than equal to n0. Now, since n is greater than equal to n0 and n0 must be greater than equal to 1, therefore, n must be greater than equal to 1. We can consider the possible choice of c1 as 1 and c2 as 6 and n as 5. So, when we evaluate this expression, c1 multiplied by n less than equal to 5n plus 4 less than equal to c2 multiplied by n using c1 as 1 and c2 as 6 and n as 5, we get c1 which is 1 multiplied by n which is 5 less than equal to 5 multiplied by n which is 5 plus 4 less than equal to c2 which is 6 multiplied by n which is 5. So we have 1 multiplied by 5 which is 5 less than equal to 5 multiplied by 5 which is 25 plus 4 which is 29 less than equal to 6 multiplied by 5 which is 30. So we have 5 less than equal to 29 less than equal to 30, which satisfies the theta expression. Therefore, we can say that the function f of n, that is 5n plus 4, is big theta of g of n. And since g of n is n, hence we say that f of n is equivalent to big theta of n. So this is the Big Theta notation which is used to describe the tight bound of an algorithm.